Okay, chemical reactions. So we've talked about chemical reactions. Chemical reactions are chemical changes. So one substance gets converted into another substance. We've got rearrangement, exchange of atoms, but the atoms themselves do not change. It's like building with Legos. You take one Lego set, you take it apart, and you build something different. You have the same number of each kind of piece at the end, they're just put together differently. So the mass of all the pieces you start with is equal to the mass of all the pieces you end up with, conservation of mass. So a chemical equation is a shorthand way of describing a chemical reaction instead of using long sentences. The general idea is that we have reactants, those are the things that react, the things we start with, and then an arrow, and just like we read from left to right, we read the equation from left to right. This is where we start, this is where we, come on pointer, where we end up. The products are what is produced. So the reactants react to produce the products. Reactants on the left, products on the right. There is a lot of information about the reaction. We've got the formulas of the reactants and products. Oftentimes we have the physical states, gas, liquid, solid, or aqueous. We're going to have the relative numbers of reactant and product molecules. And we can use a chemical equation to figure out, well, if I started with this many grams of my reactant, how many grams of product could I make? And that's a very practical sort of question. This is a big slide with very little information on it. These are called state symbols, and they're not meant to be tricky at all. G means it's a gas, L means it's a liquid, S means it's a solid, right? And we just talked about aqueous last week. Aqueous, AQ means it's dissolved in water, okay? So let's look at a reaction, the combustion of methane. Methane is a main component of natural gas. So if you have a gas stove at home or our Bunsen burners, you light them up, this is what's happening. So methane is CH4, and oxygen, here oxygen is just the oxygen in the air, and it is by itself, so we write it as O2. Those are going to react and form carbon dioxide and water. Anytime that something burns, oxygen is a reactant, because oxygen is what's necessary for combustion. So if we look at what's going on here, there's one carbon atom here, and there's one carbon atom there. Here there's two oxygen atoms. There's two oxygen atoms there, but then there's another one over here. So building with Legos, you're not going to have enough of the oxygens to make both of these things. There's also a problem with the hydrogens. There's 4 hydrogens over here on the left, and over here there's only 2. So what happened to the other 2 hydrogens? Did they turn into the missing oxygen? No. The atoms can't change. So this equation is not quite right. So we say we balance the equation. The formulas are correct, the state symbols are correct, but the numbers are not. So here we have pictures. Here we have a methane molecule and 2 oxygen molecules making 1 CO2 molecule and 2 water molecules. And when we have this combination, we can see there's 1 black ball there and 1 black one here. There's 4 red ones, 1, 2, 3, 4 red ones. There's 4 white ones and 4 white ones. So if these were round Legos, that would be kind of neat. If you took these 3 pieces, you could take them apart, put them back together, and get those 3 pieces. Okay? Pictures are awesome, but pictures take up a lot of space and they're hard to draw. So what we need to be able to do is to look at something like this and make a picture like this in our heads. Okay? I have a lot of pictures of things because I'm a visual person, I need to see it. If I can see it in my mind, though, that's as good as seeing it in real life. So how do we balance chemical equations? These are guidelines. You need to start with a skeleton equation. So you need the formulas of the reactants, the formulas of the products, and those have to be correct. Then we're going to start balancing them. And these are guidelines. There's no one set way of doing it that's going to work for every single reaction. Balance the atoms that are in more complicated substances first. You want to leave any pure elements for the end, just sort of a practical aspect. You can end up with fractional coefficients, and so you need to get rid of them at the end by multiplying everything by the denominator of the fraction. If you hate fractions, you can avoid getting fractions and not have to worry about that. Lastly, check, because it's easy to screw up. So let's practice. And we'll get a little nomenclature practice here too. Write a balanced equation for the reaction between solid silicon dioxide and solid carbon to produce solid silicon carbide and carbon monoxide gas. So first thing is we need the formulas, right? So the first thing here, well, actually, let me do this real quick. So we have words, right? The word and is like the plus sign in an equation. And that word to produce, that's the arrow. And here's another and. So we need silicon dioxide plus carbon, arrow, silicon carbide plus carbon monoxide. Silicon dioxide. So that's a molecular compound, right? Because silicon's a nonmetal, or it's a nonmetal, it's a semimetal on the nonmetal side, and oxygen is a nonmetal. So that uses prefixes. The prefix di means two. So that's silicon and two oxygens. There we are told what the state is. It's a solid. Plus, leave a space because we're probably going to have to put a coefficient in here to balance this. Solid carbon. Well, carbon is C. It's a solid. Is carbon a diatomic element? Horses need oats for clear brown eyes. No. So it's just C. In writing equations like this is where it becomes very important to get the diatomic elements correct. Carbon's not. Arrow. Silicon carbide. Well, silicon and carbon are both nonmetals. So, silicon carbide. Let's see if she'll do it. Hey Siri, what's the formula for silicon carbide?
Silicon carbide, also known as carborundum, is a semiconductor containing silicon and carbon. Do you want me to keep reading?
No, thank you. She doesn't do it anymore. The first time I did that, I asked her what the formula was, and she said it was sick. I don't know. I just found that tremendously amusing. She just pronounced that sick. Anyway, there's no prefixes in that formula, right? Silicon carbide. So how did I know that there was only one carbon? Well, if it was other than one, there'd have to be a prefix, right? And I told you that we usually leave the mono off the first one. Sometimes we leave it off the second one too. I will not try to trick you with stuff like that. So there we have sic, and that's a solid. Carbon monoxide. What's the formula for that? CO. So capital C, capital O, and we're told that's a gas. So there's our skeletal equation. Any questions? Now we need to balance it. We need to make sure that we have the same number of each element on each side of the arrow. Often what works, just from having done a lot of examples in class, is just start with the first element. So I'm going to look on the left side, and here I have one silicon atom, and I don't have any there. And I'm going to look on the other side. There's one silicon atom, and there aren't any more. So I have one silicon on each side, so that's nice. Here I have O2, 2 oxygens. How many oxygens are on the right side? Only 1. So in order to get them to balance, I can't change this formula. It'd be nice if it was CO2, but I can't do that, it's CO. All I can do is put a number in front of a coefficient. I can say, well, it must make 2 carbon monoxide molecules. Because if I made 2 molecules, then I'd have 2 oxygen atoms on that side as well. Any questions? So I've got silicon and oxygen taken care of. And then here's carbon. Carbon is by itself here, and so we wanted to leave that one to the end, and it just worked out that way as well. So on the left here in the reactants, I have 1 carbon atom. I'm going to look over here. I have 1 carbon atom there, and I have 2 carbon atoms there. Total of 3, right? So to make 3 carbon atoms on the left, I just put the number 3 in front of it. Any questions? Because if you're not understanding it now, you need to ask a question, because it's going to get more involved. Let's do another one. Balanced equation for the combustion of gaseous ethane, a minority component of natural gas, in which it combines with gaseous oxygen to form gaseous carbon dioxide and gaseous water. A whole lot of gas going on there. So first we write the formulas. So ethane is given C2H6, and that's a gas. And that's reacting with what? Oxygen. So I've got oxygen. Is oxygen a diatomic element? Yes, it is. So I need to write O2 there. And that's a gas. There's my arrow. Combines with oxygen to form carbon dioxide, CO2, says that's a gas, and water, that's a gas. Water is a liquid at room temperature, but when you burn natural gas, is that at room temperature? No, it's very hot. So that's why the water's a gas. Okay. I'm going to show you a method that can be helpful for more complicated equations. You'll notice we've got oxygens all over the place, right? And so this one can get a little tricky. So this is kind of a tally method or an inventory method of balancing an equation. Use it if you like it. If not, forget about it. So I'm going to draw a line down the middle, because that's where I'm trying to balance things. And then on the left side, I'm going to list the different elements, and I just go in order that they appear. So we have carbon, we have hydrogen, we have oxygen, and I'm just going to take inventory. So under this one, there's 2 carbons, so I'm going to write a 2 there. And over here, there aren't any carbons, so I'm just going to put a dash. This, oops, I mean to do that. This one has 6 hydrogens, so I'm going to write a 6 here. And there's no hydrogens there, so just dash. Under here, I don't have any oxygens, but over here, I have 2 oxygens. And then we're going to go over to the other side and do the same thing. So there's a 1 here, no carbons there, no hydrogens, 2 hydrogens, 2 oxygens, 1 oxygen. Taking inventory. Now what I'm going to do is I'm going to look at this carbon row and see what's my total on the left side, what's my total on the right side. So my total on the left side is 2, and on the right side it's 1. So I could fix that by making 2 CO2 molecules, right? So I'll put a 2 in front of that. That's going to change all the numbers underneath. Where's my pointer? Well, whatever. So this is going to become a 2, and this one's going to become a 4, right? Because in 2 CO2 molecules, there's a total of 4 oxygen atoms. So carbon's balanced. Then I'm going to look at hydrogen. On the left, I have a total of 6 hydrogens. On the right, I have 2. So to make a 2 into a 6, I need to multiply by 3, right? So I multiply all of these by 3. I didn't mess up my carbons. My hydrogens are balanced. Now I can look at the oxygens. Over here, I've got 2 oxygens. On the right, I have 7. How many pairs of shoes do you need to have 7 shoes? It's not a whole number, right? Because they're coming in pairs. It's got to be an even number. So you can do a fraction here. And if you like fractions, you don't need me to show you how to do that. So I'm going to show you how to do it without fractions. I call this the odd-even problem. Here the oxygens are coming in pairs, and I need an odd number of them. What happens if you double an odd number? It becomes an even number. So what I'm going to do is I'm going to multiply everything I've done by 2 to get rid of this odd number. Let's do this in purple. So I'm going to multiply that by 2. That's 6. This is 12. That's 6. 2 times 2, that's 4. This is 4. This is 8. And over here, I'm going to multiply that by 2. I haven't done anything with this one yet, so I'm going to leave him alone. Are carbon and hydrogen still balanced? I've got 4 carbons on each side. I have 12 hydrogens, right? I just doubled everything. Now, on the right side, I'm looking for 14 oxygens. So how many pairs of oxygens do I need to get 14? 7. So I got rid of the odd-even problem. So I need 7. So that multiplies and it gets 14. 8 plus 6 equals 14. Now, that might look like a lot of work. I would not recommend using this method for every equation. Any questions? Here's another one. Balance equation for reaction between aqueous lead-2 nitrate and aqueous potassium chloride to form solid lead-2 chloride and aqueous potassium nitrate. Okay, well, lead-2 nitrate. Lead-2 is Pb2+. Nitrate is NO3-. So the formula for lead nitrate is PbNO3 2. And I'm told it's aqueous, so I put AQ there. Aqueous potassium chloride. Potassium is a +1 ion. Chloride is a -1 ion. So I've got KCl. Aqueous. Arrow. Solid lead-2 chloride, so that's Pb2+ and Cl-. And I'm told that's a solid. And aqueous potassium nitrate. Potassium and nitrate. Just barely got it in. Now I need to balance this. This equation has some polyatomic ions in it. Well, it has one. The nitrate ion. Oftentimes, when there are polyatomic ions, they stay together. Sometimes they don't, but here they did. It did. So here's nitrate, and there's nitrate over there. I can balance the nitrogen and the oxygens separately, but I can also balance the nitrate as a unit because it stays intact. So here's lead. There's 1 lead and 1 lead. That one's okay. Here's nitrate. I have 2 nitrates. Over here, there's only 1 nitrate. So to balance that, I'm going to put a 2 in front of the formula. You can't change the subscripts. Not allowed. If I have 2 of these units, then I have 2 nitrates. Then I'm going to go over here, potassium. I have 2 potassiums. So then I need to put a 2 in front of this one, or 2 potassiums. And now I've got 2 chlorines, and over here, 2 chlorines. That last one kind of took care of itself. Any questions? Sometimes students say, but it looked so easy when you did it. Well, once you see what you're doing, it is easy. But until you see what you're doing, it's not. And you just practice and ask questions. Sometimes when you're balancing an equation, you can find yourself repeatedly changing subscripts. I call it going in circles. And you go in circles a couple of times and you're like, wait a minute, I'm not getting anywhere. So stop what you're doing. There's no point in just going around and around and getting larger and larger numbers. Examine your formulas. Make sure the formula is correct. Because if the formula is not correct, you may not be able to balance the equation at all. Like if I had left off the 2 here and I just had Cl, there would be no way to balance this. Then, if your formulas are correct, start over and start in a different place. Here I was starting with lead and just working my way through. If that gave me unsatisfactory results, maybe start with potassium or start with chlorine. Start somewhere else. Okay?